We all have that one student. They memorize every definition, they ace the multiple choice midterm, but the moment you put a real-world case study in front of them, they freeze. You explain it again, and they just stare blankly. This is where the traditional didactic model, where the professor speaks and the student listens, reaches its functional limit. That traditional model is being strained by three overlapping forces: an acceleration of information volume that exceeds human processing speed, rigid biological limits on human memory, and the sudden arrival of generative AI. If a student can rely on an AI for instant retrieval of facts and definitions, a professor acting as a mere information delivery system provides little value to the learner. Navigating this shift requires faculty to stop thinking of themselves as lecturers. The goal is to become an engineer designing a cognitive environment where knowledge is a direct byproduct of the classroom architecture. To build that environment, we have to look at the biological hardware constraint driving student failure: cognitive load theory. Think of the student's brain as having a processing center, a working memory. It operates like a very small workbench. This workbench can only hold 4 to 7 distinct pieces of information at a given time. If you add an eighth, something drops off the edge. When we lecture aloud while simultaneously forcing a classroom to read dense text on a presentation slide, we flood that workbench. We create extraneous cognitive load, instantly maxing out their processing capacity. When a student stares blankly, it rarely means the subject matter is too complex. It means the instructional design has overloaded their biological working memory. You do not possess more raw processing power than your students. Contrast that fragile workbench of your own brain. As an instructor, you have a long-term memory that functions like a massive, deeply organized warehouse. You just have decades of pre-assembled schema sitting on those shelves, ready to be pulled instantly to the workbench to solve problems. This mechanical difference creates a dangerous psychological trap, known as the expert reversal effect. The exact conditions where experts thrive, unstructured, open-ended problem-solving, cause immediate cognitive failure in novices who lack those internal schemas. A beginner requires strict, step-by-step instructional rails to function. Placing those same rigid rails on an expert, however, causes immense frustration. Because you are an expert, your intuition about how to teach is biologically misaligned with the hardware a novice uses to learn. You cannot transfer knowledge like a digital file. Knowledge is an architecture that the student physically builds in their own mind. Educational philosopher John Dewey argued this construction requires a specific catalyst: cognitive conflict. You have to present a problem that is impossible to solve using their current methods. This creates a recognized deficit. Only after they feel that friction do you introduce the new theory as a tool to fix it. Lev Vygotsky mapped out exactly how that processing occurs through a mechanism called interiorization. Internal thinking is driven by external speech. Students must be forced to argue, explain, and vocalize data to physically wire it into memory. This means we have to break the expectation that every problem has one simple, dualistic answer. We have to push them into a state where they realize outcomes depend heavily on context without causing them to panic. A quiet, compliant classroom is cognitively dead. Genuine learning demands friction, vocalization, and guided struggle. First, we have to stop fragmenting courses into isolated topics, like teaching syntax on week 1 and algorithms on week 5. The blueprint that maps these constraints, the small workbench and the need for struggle, into a single course structure is the 4CID model. The first quadrant is learning tasks. From day 1, students face a whole task, a complete project scaled down to a simplified version. The second is supportive information. We deliver the theoretical why prior to the task to build necessary schemas. The third is procedural information. Checklists and step-by-step hints are provided specifically during the task, right when they are needed, keeping their working memory unburdened. The fourth quadrant focuses on part task practice. We isolate and drill only the specific microskills that require total automaticity, like keyboard shortcuts or basic math. This progression relies on scaffolding. You start by providing a fully solved example, step down to a problem with missing variables, and finally require a blank slate execution. This 4-part system prevents cognitive collapse by offloading routine procedures to focus the student's limited working memory on the whole task. If we regulate the cognitive environment, generative AI ceases to be a threat that we need to block. In a properly architected course, AI becomes Vygotsky's more knowledgeable other, a personalized, around-the-clock tutor sitting next to every individual student. But this augmented reality demands a shift in our evaluation methods. We have to move past testing rote memorization. All grading must shift toward authentic assessment. We must evaluate exactly what a student can do in a simulated real-world situation, rather than what they can repeat back on a test. Faculty are shifting from being the primary source of information to being the architects of the workshops where that information is applied.